All right, welcome back, Physics 30. Today's lesson is basically beginning of Unit C, Part 2. So far, we mainly study about the light because it is important to understand some matter as wave for the first part. That is Unit C, Part 1 booklet, all the way to Young's double slit experiment. Now, when it comes to Part 2, we're going to look at matter as what we already learned from chemistry, particles. Now, of course, our main focus, which is what you see over here, is photon. And that concept came in 20th century when groups of scientists start finding some evidence that in fact light is composed of particles instead of waves. And for this unit, we are going to learn about various different scientific discovery done by other scientists and how that theory is accepted or disproved and yada yada, those kind of historical perspective of it too. And eventually, we're going to learn quite some mind-blowing facts. Like subatomic particles, like electron, protons, neutron, they are behave as a particle, but if we go quantum situation, which is smaller scale than that, it's in fact wave. And of course, right now it's hard to understand the whole big picture of it. In fact, even now, nobody truly understand what is the quantum physics is. So we're gonna focus on things that is important for high school kids and or physics 30 course. That's what we are going to focus. So first thing first, in the early 20th century, there are quite some experiment was done, but a certain experiment deal with specifically about amount of light. And when we talk about light, specifically we're talking about EMR, electromagnetic radiation. And that experiment basically found that EMR is composed of tiny particles that carry energy. And that is what I like to call photon. And this is the beginning of the two groups of scientists who versus about is light a wave? Is light in fact composed of particle? Those kind of situation. And in the end, if I tell you long story short, EMR, any type of light, actually have both wave and particle property. And from now on, this is what we're going to call it, wave-particle duality. If I visually write down or draw how photon will look like, and by the way, photon is one of the term that we're going to learn today too. It is considered as a particle of light. And here's what I'm going to explain to you. How can light become a particle? First thing first, a lot of people think particle as a sphere, three-dimensional sphere. Like electron, proton, neutron, those guys are particle. Electron, people used to put negative inside of this circle, positive, something like that. To be precise, if it's three-dimensional situation, we call it sphere. Now, photon, so light, in part 1 of the Unit C, we in fact discover some of the experimental discovery by Young's double slit experiment and the others. They use refraction and reflection, which light does have it, and that proves that light has waves. So photon, generally describe it in this way. Imagine a capsule, like a medical capsule. You know, the one that if you consume, it's going to be dissolved and then whatever the liquid inside can come out, something like that. A good example is fish oil, tablet, or any type of omega-3, which you can find it from lobster, king crab, those kind of thing. Imagine that little wrap, if you will, or shell, if you will. Inside, we have certain frequency and wavelength that is trapped inside. So wavelength is basically trapped inside of this shell. And photon theory is actually came up from that as soon as some groups of scientists discover the property of particles. One of the good example is Rutherford and gold foil experiment. And you're going to learn about those again in a bit future. The long story short, this is a formula that they figure out. Each of these particles basically carry energy, and whenever these particles bombard on surfaces like metal, they emit electron, and that's how we can, for example, use solar panel into an actual technology generating electricity, or how this light can affect some atom and turning into ion, something like that. So, long story short, particle of light is known as photon, and photon carry energy or have an ability to give an energy. We call that photon energy. And the calculation that you can do is energy of the photon is equal to hf or hc over lambda, because this h is our new constant that is known as Planck constant. Planck constant, Planck is one of those well-known physicists who, how can I say, also play a huge role when it comes to talking about the time and concept of time, general relativity. He played a huge role for Einstein discovery too. But long story short, we need to understand in high school level that h is Planck's constant. And Planck constant is given to you as 6.63 10 to the power of negative 34, and unit is joule second. Now, there is another value that you can use too, and I'm going to explain to you why there's two. You can also use this, 4.14 10 to the power of negative 15 eV second. Both are given in your data sheet. And now you may wonder, Mr. Kim, why do we need joule second and electrovolt second? It's because, let's think about it. Joules, when it comes to a subatomic level or any type of ion level or nano level, whatever the small scale you can think of, not the quantum. I'm going to talk about that way later as you go through unit C and D. But long story short, when it comes to small object, let's think about it. Small object that is moving can collide. That means you can give a little bit of a kinetic energy. Now, think about it. The small object, like electron's mass is 9.11 10 to the power of negative 31 kilogram. So that means even if the speed is really, really fast, which you cannot exceed 3 10 to the power of 8 meter per second, but in any case, even if you collide, the energy amount will be really, really small. And look at this constant too. 6.63 10 to the power of negative 34. That is really small number. So here's the thing. Scientists find out some of those conventional way. We decided that 1 electrovolt, this is a new unit for energy. But you may notice it's not joule, it's an electrovolt because it's conversion of how much electron can give you energy. Think about it in that way. And the conversion is like your basic element charge, 1.6 or 10 to the power of negative 19. The way that you can understand this is kind of like this. 1 dozen is equal to 12, whatever the number, right? Think about similar comparison between those two. Instead of saying, oh, I have 12 pencils, you can say, oh, I have 2 dozens of pencils, something like that. It is a way of showing as a bundle. You can use it for the unit too. So, 2 things that I want to point out to you. Let's talk about relationship first. If you look at this frequency and energy relationship, whatever the higher frequency that I have, I'm gonna focus this here a little bit. There you go. Sorry about that. Whatever the frequency value that you have, if I have higher frequency, you will expect higher energy. So if you think about our previous Unit C Part 1, you will notice that we learn about the wavelength and frequency band, basically. Like, for example, the highest wavelength is radio wave, something like that. So if I look at the relationship between energy and frequency, whatever the object that have really high frequency of EMR, it has high energy that can be coming from them. So for example, gamma ray, X-ray, UV ray, they have high energy and that can become to our cell if we contact them. For example, why people want to have a UVB protective sunscreen is whenever you go to Mexico or something like that, is because UV light can actually destroy your skin cells' DNA because it is quite powerful. So you may need to understand the relationship. So what does that tells you? If you look at the wavelength perspective, whatever low wavelength will give me high frequency, thus you will have high energy. This is one of the reasons why radio wave, which is really high wavelength, will make this entire fraction go really low. Thus, my energy will go low in that perspective. So know the correlationship between E and F and then E and lambda. That's what I want to point that out. Another thing, photon energy, like I mentioned, is quite small. So that's why we use electron volt, which is known as EV, because we're going to learn tomorrow that is known as photoelectric effect, how much photon that is collided to metal, something like that, it creates some electric energy. And when it comes to electron, we measure voltage for potential difference, right? So think about similar category as that. Now, let's talk about relationship between EMR's intensity. So how much bright, how much dim. Let me go through this part using two different diagrams over here. If something is quite bright, or fancy way of saying it's very intense, high intensity, and low intensity, you may know that if it's high intensity, there will be a lot of photon because a lot of light is emitted. So you can consider that high intensity means large number of photon. If it's dim, however, it's small amount of photon. So mathematically, those relationships can work like this. The total energy that EMR can produce is equal to how much number of photon times by how much energy can be produced. So you can think that intensity does give you a correlation between high number of photon versus low number of photon, depends on its brightness. So let's do some class example over here. Number 1, determine the total energy of 71 photon. Number is given as 71. Answer in EV. So energy is what I need to get. Whatever blank blank EV. And we don't know that. We only have one clue. Basically, some wave pattern and distance that is given. 650 nanometers taken from the starting point all the way to the end over here. Now, although it's talk about the wave, don't freak out. It is a wave-particle duality. We're slowly going to move on to our particle. But like I said, even if it's particle, think about some wave that is trapped. So here's what you need to do. Whenever you see this graph, identify the pattern. Go up, down, and return. That's one wavelength. Up, down, and return, second wavelength, up, down, return, third wavelength. So in fact, here's my one particle, second particle, third particle. That is what I see. So 615 nanometer, if I divide it by 3, then I can truly have one wavelength worth of it. So let's do some calculation. 650 divided by 3 will give me 116.66666 and return. So in order to make a precise amount, that's nanometer, I'm gonna report it as fraction because I don't want to round up. 650 over 3 nanometer is what I have, and that's basically what it is in here. Now the energy, first thing first, E is equal to HF, but as you may know, HF, F is reciprocal of actually not reciprocal, sorry. We can use our universal wave formula. V is equal to F lambda, which will in turn turning into C is equal to F lambda, and thus we know that F is equal to C over lambda. So if I substitute this, what I see on the right side fraction, into this system, then you know that it's HC over lambda. That's how this formula on the very top section of the page 36, you can see it on the top. But in any case, let's punch some number in. 6.63 10 to the power of negative 34 joule second. 3 10 to the power of 8 meter per second divided by wavelength, which is 650 divided by 3 10 to the power of negative 9 meter, because it's nanometer. And we are going to punch the number in. I purposely did joule. You can directly use electrovolt, but the reason that I'm doing is in joule is so that you can you know how to convert back and forth. It is an important skill. So if it's in joule, we know that the total energy from this light is 9.18 10 to the power of negative 19 joule. But the thing is this, if you want to convert into EV, you need to divide it by our elementary number, 1.60 10 to the power of negative 19. Then you have about 5.74 electrovolt. Actually, I rounded up wrong. The significant digit is 2 significant digit. So 5.7 electrovolt will be good. Honestly, in diploma, it is highly likely it will be 5.74 because A, B, C, a point BC, so it's a 4 column, and if you use significant digit rule, this is countable number, and we have a measure value that is 3, so technically this is on the right track, 5.74. Let's do another example. Now you will see some of the unit that you haven't seen for a while, like W. So 90.0 W means watt. Watt lamp emits 250 nanometer, which is equivalent as 1.20 10 to the power 15 hertz of UV ray. Determine the maximum number of photon emitted in 10 seconds. So whenever you see the unit W, that means that unit is power. So you need to understand that 90.0 what is my P. Sorry, my dog is going crazy. All right, where were we? So the power is 90.0 watts and time, which is also given as 10 seconds. Wavelengths given and frequency also given. Long story short, it doesn't really matter which one you choose. If you want to do wavelength or use frequency, because in the end we are going to use energy to figure out the final answer, the maximum number of photons. So last time I used wavelength, so why not I use frequency for this question. First thing first, power and energy relationship. You do not need to memorize this formula. In fact, the formula is given under the section of momentum and energy. Work is equivalent of energy, and then P is equal to W over T. So if I rearrange this entire two formula situation, delta E is equal to power times delta T. Power unit is watt, T unit is second. So 90.0 watts times by 10.0 second is equivalent of 900 joule. So from that concept of power, we could figure out the energy amount. Once you get that, now it's relatively easy. We know that this is total energy. And we are trying to find NHF, whatever my energy that can come out from the EMR with the 250 nanometer UV radiation. So the number of mole is equal to ET over HF. Since we're using 900 joule, it's a good idea to use unit with the joule and second. Like this. So number of mole is equivalent to 900 divided by 6.63 10 to the power negative 34 times by 1.20 10 to the power 15 provides me, and three significant digit in this case, 1.13 10 to the power 21, oops, not electron, photons. That's what you can do. That is my today's lesson. Your to-do list is basically page 37 of your booklet and page 38 of your booklet.